Okay, g'day students. To today's lesson on hydrocarbons. Today we want to deduce the structural formulas and apply the IUPAC rules in the nomenclature of organic compounds, which is a parent chain up to 10 carbon atoms, with simple branching just for alkanes, alkenes and alkynes today. Now, the IUPAC is the International Union of, pure and applied chemists. Okay, so if I think about hydrocarbons, most of our hydrocarbons we get from crude oil, and you can see that crude oil can be distilled and to be separated into a variety of other different sorts of hydrocarbons based on the boiling point. Now, if we think about classes of organic compounds, a family of compounds which can be represented by one molecular formula is called a homologous series. Homo for the same, logos for words. Now, homologous series have similar structures, a pattern to their physical properties, similar chemical properties, and the same general formula. So if we have a look at, first of all, the alkanes, so we've got methane, ethane, propane, butane, and so on. Now, we're just going up to the first 10, so here are our prefixes here. So after butanes, pentane, hexane, heptane, octane, nonane, and decane. Our formula is for alkanes is what? CnH2n plus 2. So if I were to choose butane, and what is it? Cn, so C4, and then H2n plus 2. Well, 2 times 4 is 8, plus 2 is 10. So the formula for butane is C4H10. Now, butane just looks a bit like this on the right. That's a bit hard to see. Now let's have a look at this molecule up on the top right corner. We've got 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. So it's an octane. And what else is important to work out the formula? So we know it's what? CnH2n plus 2. Well, C8, now 2 times 8 is 16. And 16 plus 2 is 18. So if I were to count all the hydrogens, I should see 18 hydrogens there. Okay, now sometimes these backbones may have branches off them, and these branches we call an alkyl group. So the existence of 2 or more distinct compounds with different structures, but the same molecular formula is called isomerism. So 2 or more compounds with the same molecular formula are called isomers. Now, if I have a look at pentane, which is C5H12, I can have a variety of different structures that exist as C5H12. Now, the first and most obvious one is just a straight line carbon chain, and that's just going to be C5H12, and it's a 5 carbon backbone, so we'll call that a pentane. But when we get these groups on the side, we're going to actually name each of these after the carbon backbone. So we'll go 1, 2, 3, 4. If I want to look at this quick, I can see that this is a 4 carbon backbone, and it's got a little group off the side, and it looks like a methane. It's close to methane, CH4. But it's a CH3, so instead of methane, we're going to call it methyl. So a methyl group is an example of an alkyl side chain. Now, alkyl side chains have 1 less hydrogen than the corresponding alkane. So to name the side chain, you just swap the ane with the il. So in this case, we've got a 2-methyl butane, because it's said to be 2-methyl because the methyl group is on the 2nd carbon in the butane. Now let's have a look at the next one. It's still an isomer of pentane, but we've got a propane now, haven't we? We've got 1, 2, 3 carbons, so it makes it a propane. But in this case, we've got 2 methyl groups, and 2 methyl groups on the 2nd carbon. So it's a 2,2 because there's 2 methyl groups there. It's a dimethyl, indicating that it's 2 methyls. So 2,2 dimethyl propane. For naming this particular isomer of pentane. So let's look at some rules for naming alkanes. So all but the most complicated alkanes can be named using the following steps. So first of all, identify the longest continuous carbon chain. Now this is the parent alkane. Now carefully check to see that the longest chain, which is the longest chain, because sometimes it's not drawn in straight lines. So you can see what's happening here. So that's pentane, isn't it? It's got 5 carbons in a row, and it's got this methyl group on the 3rd carbon. So this makes it a 3-methylpentane. But this is also a 3-methylpentane because the backbone has been drawn at right angles, hasn't it? So you can see that we're starting off here at the first one and we're going this direction. So we still see a methyl group on the 3rd carbon in this pentane. Now we number the carbon atoms in the chain from the end nearest to the first branch point, so that the first alkyl side chain will have the smallest number. So what does that mean? It means we see the first branch point and we're going to start the numbering from the closest to the end. So that means this is going to be number 1 rather than this one number 1, because this is the closest side. First, it's the closest branch point. So we place the number and the position of each alkyl side chain before the parent's alkane name. Now, if 2 identical side chains are present, we're going to use the prefix di. If there's 3, we're going to use tri. So you could get a trimethyl, for example, or even a triethyl if it's like an ethane but dropping a hydrogen. Now, each side chain is still given a number to indicate its position on the carbon chain, and the numbers are separated by commas. Now, if there are alkyl side chains of different lengths, for example, methyls and ethyls on the molecule, you list them in alphabetical order at the start of the name. So each side chain is given a number to indicate its position on the carbon chain, and the numbers are separated by commas. So we write the name as a single word with hyphens to separate the numbers from letters and commas to separate numbers. So let's look at our 2,2-dimethylbutane. So our first branch point is closest to the left-hand side. Now I can see 2 methyl groups, and they're 2 methyl groups on the 2nd carbon. So it's 2, 2. It's a dimethyl because there's 2 methyls. And then it's a butane because I can see 1, 2, 3, 4 carbons in the backbone there. Okay, let's have a look at the next example. We've got a 3-ethyl 2-methylpentane. So we're going to label the ethyl first because it's alphabetical, and this is our ethyl. It's a lot like ethane, isn't it? We've got 1 less hydrogen than ethane, so that's a 3-ethyl. It's on the 3rd carbon, so there's our 3-ethyl, and then we've got a 2-methyl, which is our methyl group. It looks like methane, but 1 less hydrogen. So that's going to be on that one. So it's a 3-ethyl, 2-methyl, and it's a pentane because there are 5 carbons in this backbone. Now, a cycloalkane is what it sounds like. It's just in a cycle. And carbon atoms can form not only chains, but they can form rings. So when we name these cycloalkanes, we're just going to add a cycle in front of it. But if we have a look at cyclohexane, for example, you can see that there are 2 less hydrogen atoms than your typical hexane, and that's because you've got a carbon-to-carbon bond there where there would normally have been 2 carbon-hydrogen bonds instead. Now, let's think about some unsaturated hydrocarbons, and these are called alkenes and alkynes and so on. So hydrocarbons which contain a double bond between a pair of between a pair of carbon atoms are called alkenes. Now the simplest is ethene, and so the general formula of alkenes is just CnH2n. So the first 3 are ethene, propene and butene, and you can see that the presence of this double bond indicates that this is an alkene. Okay, similar naming as the alkanes, say methane, ethene, propene, butene, pentene, hexene, heptene, octene, nonene, and decene, for example. So the stem name from the longest chain containing the double bond, the ene suffix. Now, a longer chain may be possible, but if it doesn't contain the double bond, it can't be used for naming. The location of the double bond is indicated by the number of the atom which it starts on and a hyphen before the stem name. So the lowest number possible is needed. So this would be but1ene if I were to name that more precisely. Now, benzene's an interesting one. So benzene displays what we call resonance, and what resonance means is just it can be, we can draw this electron configuration or the bonds a couple of different ways. So essentially you can see that we've got a single, then a double bond. But because of all these delocalized electrons, that's continuously changing. So it comes up with this ring structure. And benzene's a bit of a nasty chemical. And so we will hear a bit about this in carbon chemistry. It's also quite a useful chemical. What do we need to know? So we just represent benzene as this ring structure, and note that essentially each carbon-carbon bond is essentially 1.5 carbon covalent bonds rather than a single, then a double, single, then a double. And so you'll often see it with just a dotted line around the inside as well. Now, alkynes just contain triple bonds. So if you have a look here, we've got ethyne, propyne, and butyne, and we can see that, hey, we've got just triple bonds going on here. Okay, so alkynes are hydrocarbons that contain triple bonds. It's going to be very linear around that triple bond, and there's going to be no room for rotation around that triple bond because those two carbons are held very firmly in place. So the general formula for an alkyne is CnH2n-2. It's similar naming to alkenes, just with the -ine suffix. Now the simplest is ethyne, which is what? C2H2. Now alkenes and alkynes, remember, are called unsaturated hydrocarbons because it's possible to attach a hydrogen by breaking that double or triple bond. Now the naming rules, you name according to the longest carbon chain. So if we have a look up here, what do we got? 1, 2, 3, 4. You can either go 5 down here or 5 there. Doesn't really matter. And then we know that this is going to be some sort of pentyne. Now, note the position of the triple bond. It's in the first one, so it's going to be a pent1-ine. Now we'll name the alkyl side chain and position. You can see that it's on the 4th carbon, so it's going to be a 4-methyl pent1-ine. And then you just list the alkyl side chains alphabetically at the start of the chain. Numbers separated by commas, remember that. And you combine your hyphens to separate the numbers from the letters and the commas to separate the numbers. So, are you able to deduce the structural formulas and apply the IUPAC rules in the nomenclature of organic compounds in alkanes, alkenes, and alkynes? When you've done that, please work on your mastery questions.